Hello. It's been a little bit hectic, and I would have liked to have gotten this done earlier, but I've been driving around and trying to get things done. So I appreciate your patience. Now, um, uh, this is really, in terms of material, fortunate that we're not going to spend as much time as maybe is on the calendar, because this topic is um, summarized very briefly. There are a lot of calculations that I consider, because we are in the 21st century, to be completely and utterly outdated, and that I'm not going to address. Instead, I want to focus on what does all of this mean? What is it good for? Uh, we will later use the standard deviation, for example, in every single um, of our calculations in inferential statistics, maybe not correlation and regression, but almost everything. All right, um, we know how to calculate the mean, the average, and the median. Okay, so what we have with that, with measures of center, is this: potentially huge data sets, huge data sets, maybe 100 million people or 150 million people, for example, that are voting. And then a single number that's going to try to represent or give us information or insight or understanding of this huge data set. The average age of voters, all right, of all the people that voted, 150 million people, what is their average age? Well, a reasonable question to ask is, wait a minute, there's a huge amount of data. How is that single number, one number representing 150 million numbers, or trying to get us to understand 150 million numbers? Is that doing a good job? Yeah, and that's where we can use the new tools called, which are summarized as measures of variation, to get a little bit of a sense of how good and we're going to focus on the mean. How good is the mean at describing the data? All right. So take a look at these three sets of data. Okay. Here, the mean, the sample mean, X bar, is 5, and the sample standard deviation is 0. Here, the sample mean, X bar, is again 5. And now the sample standard deviation is approximately 1.2, clearly different than the first. And here, the standard deviation, or excuse me, the sample mean, X bar, is again 5. And now the sample standard deviation is about 3. Okay, 3 different data sets, clearly different, but each has the same mean, right? The same mean. And so a good question to ask is, does the mean represent, in the sense of, does it give us insight into the data equally well in each of the three cases? Do we get a picture that is just as accurate here as it is there, as it is over here? Yeah, does it? So the standard deviation is going to be a tool that we'll use in a variety of ways. And one way to think about the measures of variation is that they give us a way to answer the question, how good is the mean? Right? Now, kind of separate, but just as a very uncomplicated tool, is the range, right? It's really, how far do the data go spread? They go from here to there. Okay, that gives us a rough idea of what we're dealing with, right? So the range is the maximum data set minus the minimum data set. We already saw that as part of our calculation for class width. What we were taking is the range and dividing it up into equal numbers, or equal pieces, which we then called class width, or bins, right? So the range just says it goes from here to there, from here to there, minimum to the maximum. How far is that? So uncomplicated formula, calculate the maximum, calculate the minimum, subtract those two. The data go from here to there. This is the spread. All right. So of all of the things that we're going to look at, for us, the most important is the standard deviation. And a reasonable question to ask is, deviation from what? Right? Deviation from what? And so if we're framing measures of variation in terms of the question, how good of a job is the mean doing in representing a potentially very large data set? Really what we're asking is, or a way, not really, but a way to rephrase the question is, on average, how far do the data deviate from the mean? Yep. If the data, don't deviate from the mean, then the mean is basically giving us a good representation of the data. If the data are far away from the mean, well, then the mean is maybe not the best representative, or maybe that tells us something at least, okay? So deviation, the important word is not included here. It's just called deviation. It is deviation of data or by data from, drumroll, the mean. Deviation by the data from the mean. From the mean. How far away do the data fall from the mean? What is the difference between the data and the mean? That's what we're looking at. It's all about the variation from the mean. All right. Tiny little graphic. The rest are better. Apologies. Here is the variance. Excuse me. This is the population standard deviation. We're not going to deal with this formula. What I want, strictly speaking, we're not going to deal with any of these formulas. In our lab, we're going to press a button and Excel is going to calculate it. So I don't really care much about, I'm not going to ask you to do anything by hand. In class, there's time, or on a quiz or anything like that, there's time, there's plenty of time when you're doing homework on Pearson. I think I've asked a couple of questions just to, again, feel what is Excel doing when we press that button, right? What I want to emphasize here is that this little S with a little hook on it, a horn, is the lowercase Greek letter sigma, and it stands for standard deviation. And so this is an S, a lowercase sigma. And again, we have mu, the population mean, and we have the capital N, which is, again, the number in the mean. And there's the formula. Don't worry about that. Again, there's going to be I have a detailed formula coming up. And don't even worry about that in terms of memorizing it or even ever doing it by hand. Not in class, not on a quiz. What does it mean? Yeah. So what we are going to be using is sample standard deviation, and I want to just skip down here and look at sample standard deviation. Is, again, not a Greek letter, it is the letter S. I like to use STDEV for standard deviation, for sample standard deviation, because that's what's on it. That's what Excel uses. I like that. So STDEV. We will be perfectly fine with S. I will accept either one of them. And just again, here's a whole big formula. Don't worry about that. It's going to be broken down. But the differences are that it's not mu, it's X bar because it's a sample and it's a lowercase n. And for theoretical reasons, it's not lowercase n, it's lowercase n minus 1. And then here is another thing. We're not going to deal with variant. We're not going to deal with variance. Sorry, I skipped there. Don't worry about that. Here's the variance again. We're not dealing with it at all. So I'm not emphasizing it. Really, what I'm doing here is this. What is the name of the set? What are the names of the symbols? There's S for standard deviation and X bar and N. All right. But here's the idea of standard deviation. Standard deviation. First, calculate the mean of the sample, right? X bar. So here we have X bar. Add up the variables, capital sigma. Notice how different capital sigma is than on lowercase sigma. Capital sigma, sum, add up the variables, divide by however many there are. Okay, and this should be lowercase n. The text has got a misprint in there. I'm copying this from the text. I just realized lowercase n, but add up all the numbers, divide by however many, right? And then do this, right? The question is, how well does the mean represent the data? And a rephrasing of that is, how far away are the data from the mean? By how much do the data deviate from the mean? What is the difference between the data and the mean? So here we have the data, and then we have the mean. And we're going to see for each data point, how far away is it from the mean? How far away is it from the mean? Okay, so we just take for each data point, subtract the mean from it, and say, oh, this one is this far away. Oh, this one is this far away. This one differs by this much, right? So again, the big picture is how far away, on average, are the data from the mean? Because we want to know, is the mean doing a good job of representing the data? That's what we'd like to know. That's where we're headed. All right. Now, for theoretical reasons, we have to square those differences, right? This is how far away this data point is from the mean. Can't leave it, have to square it. Okay, so we're going to get these SSX, which is the sum of the squares. All right, so for theoretical reasons, we have to square how far away each data is from the mean. And then we take the average, right? We add up all those square differences and then divide by however many there are. And for a different theoretical reason, we're going to divide by not n, but by 1 less than n. So we had n of these differences, but we divide by n minus 1 for theoretical reasons, right? And so that gives us, on average, how much deviation there is between the data and the mean, on average, right? We added up all of these numbers and we sort of divided by however many there are. Oh, right, I'm making this up like, oh, wait, we squared those numbers and then we found the average. So what do? How do you undo, we're in a bind here. Oh, deadline. How do you undo squaring? You kind of throw a square root on it. Again, I'm just telling a little story, but we can imagine that that's what we're getting is, right? So the variance is closer to that idea of an average deviation from the mean, standard deviation, both of them a little bit technical. Okay. So you can see here for this data set, all of the data is 5. 5, 5, 5, 5, 5, 5, 5, 5, 5. There's 8 of them. All right. How much deviation is there between the 8 5s and the mean, which is 5? Nothing. No deviation. There's no difference. All right. Whereas here in the second one, we have 4 4 of the data, the 4 of the data are 5s, 2 of the data are 4s, 2 of the data are 6s, 1 of the data is a 3, and 1 of the data is a 7. And when you put all that together, the mean is again 5, but now they do differ, right? There is a difference. And then over here is a very dramatic example, right? A very dramatic example where we have 3 2s, 3 8s, 1 3, and 1 7. They average out to be 5, but I don't know, 5 doesn't, it does work out to be the average, but none of those numbers are 5. None of them are even really terribly close to 5. So if I were to say 5, I mean, it's just not giving me a picture of the data. Over here, beautiful. Here, good, right? So, and you can see as the standard deviation increases, what happens is the data begin to spread out from the mean. All right. What can you do with standard deviation? If you have bell-shaped data, which we'll later call normally distributed data, then you can say, well, about 68% of the data are within 1 standard deviation, 95% are within 1 or 2 standard deviations of the mean, and almost all the data, like 99.7%, are within 3 standard deviations. We're going to do a workshop on this, no worries. Okay, so deviation from the mean, average deviation from the mean. Does the mean do a good job representing the data? All right, not the formula.